Welcome and hello. Good evening, world. Hello, world. Getting things up here. I can turn that off, I think. So, hello, world. Welcome. I hope everyone is doing well. I am, I don't know why I'm so tired, man. I don't know what it is. But I would like to continue from where I was previously, which was working on ye old Clojure. And what was I even doing? So basically the plan is, sorry, I just had a thought about something at my job. I remembered something about testing, and I was like, no, forgive me. I got one of the things about my job is like I often am thinking about stuff when I'm home about my job. It's just a lot of difficult and uncomfortable situations. I mean, that's part of a job, right? It's not like I'm not complaining about it, but it's just, it's distracting. Like I just want to come home and do something else. Like I can't. I can't. Just there was something I worked on that didn't get passed through due to quote unquote testing for testing reasons, testing purposes. The client, I guess, somehow wanted more testing, and they basically just never did not accept the thing that we built for reasons that are just beyond me. It's not like it was tested. It just wasn't tested in exactly the way they. I don't know. It's confusing. It doesn't make any sense. It's not like I'm not even really in constant communication with these folks to really even, discuss it, talk about it, or what have you. Unfortunately, I'm also within the same breath. I was looking at agile sort of methodology or ideology, and part of the thing, it's like I'm suddenly longing because one of the things you do in agile programming is that you're in constant communication with sort of all relevant parties, and so in theory I wouldn't feel like this, where it's like, oh, I've got this thing and you gotta hash it out, you gotta mull it over, and you gotta talk to each other about it, you gotta address it, come to some kind of conclusion or discussion about, like, okay, you wanted this thing built, it was built, and now you want to use it, but you don't want to use it without quote unquote enough testing, but you also aren't in enough communication with the person who could test it to even approach how much testing would be enough testing and what would be a viable option to not make this person feel like they wasted their time building this thing that no one's going to use. Oof. 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 Anyway, forgive me. Forgive me my self-indulgent ways and absolute refusal to put down the things that I was working on. The failures, my failures in life. Just kidding. Wouldn't that be great if I could look at all my problems as just absolute failures? Alright, so this problem. Modified Kaprekar numbers. So we're going to go through 8 problems, not today, but just 8 problems total before we work on the next thing. But we'll mix them up between easy and mediums. Probably not do any hard problems in Clojure because the hard problems are sort of hard regardless of the language that you're using. These problems are going to be hard for me because I don't know Clojure. At least I don't know particularly well enough to be like very, I don't know nimble with my coding. But the problems themselves, in theory, are sort of trivial. Like the easy ones are kind of like trivial, and then the mediums are a little harder, but relatively easy still. And the hards are kind of difficult. Some can really get you stumped for a while. Usually, I mean, you put your mind to it, you'll eventually solve it, but the hards can definitely be showstoppers. Pretty tough. Modified Kaprekar number is a positive whole number with a special property. If you square it, then split the number into two integers and sum those integers, you have the same value you started with. Oh wow, amazing. Consider a positive whole number n with d digits. We square n to arrive at a number that is either 2 times d digits long or 2 times d minus 1 digits long. Split the string representation of the square into two parts. Really? Is that how that works? If you have the number of digits, you square it, you're going to have twice the number of digits. Yeah, I suppose that's true. You'd have like something like this. It's Kaprekar numbers. HackerRank. HackerRank. It would be like you have, you know, like a sub 0 times 10 to the 0 plus a sub 1 times 10 to the first dot 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 to like a sub n 10 raised to the n, right, which is like I equals 0 of a sub I 10 raised to the I to the n, and this is just some value v or x, what do you want to call it, some number. And so if you had to take a number v times w, right, that's going to be this thing times the other. Sounds a very similar for another sequence. And some m, n, m. And if you note very carefully that the dominant terms here are going to be this, you could say this is sort of like the dominant term is an times am times 10 raised to the m, 10 raised to the n plus m, right? But then you know that an is, and am are both between 0 and 9, which implies that what's that called, multiplication of these two? What do they call that? The product of these two things is, I did that wrong, 81. So this is two characters, two digits, which implies that which is kind of like approximately, well, yeah, I guess that implies that number of digits actually these can't be 0. right? It's either n plus m plus 1 or just n plus m. If this has, because this has either 1 digit or 2 digits, so this is, if this is 1 digit, then you're looking at, you know, this just becomes like 9 whatever, the 1 in front, it just becomes a 9. It's already the same number of digits. Now I actually think if this is 0 and this is 0, you would get 0, 1 or 2. Actually, yeah, it's the other way around. It's my mistake. Depending on the power of this 10 here, right? It's either n plus m plus 1 or n plus m plus 2. And then we say let d be number of digits of v, then d, so d is going to be, it's going to be n, I think minus, I think it's going to be how many digits? So 0 to n. Each one of these is another digit, each of these terms. There's n plus 1 terms. That's a lot of digits. So n with respect to d, so that means that then d plus 1 equals n. Yeah, that's kind of a tricky thing, but basically, no. Is that right? Wait a second. Or d equals n plus 1. Did I get that right? Yes, I think that's right. D equals n plus 1. Yeah. Oh, that's interesting. Like you have 10, d would be 2, 10 would be 1, and then 10 raised to the 0 is just times 0. And v squared would imply 2n plus 1 or 2n plus 2, where d minus 1 equals n digits. So 2 times d minus 1 plus 1 or 2 times d minus 1 plus 2, which gives us 2d minus 1 or 2d digits. Kind of involved, not totally formal of a proof, but exactly what they've described here. Yeah, that's how they arrived there. You could probably formalize that if you really wanted to. That's kind of neat. It's kind of cool. So we know how many digits you can have for when you square a number. Neat. Split the string representation of the squares into 2 parts, L and R. The right-hand part, R, must be d digits long. Left is the remaining substring. Convert those substrings back to integers and add them and see if you get n. For example, if n equals 5, d is 1, n squared equals 25, split that into 2 strings, convert them back to integers, 2 and 5. Test 2 plus 5 equals 7, it's not equal to 5. So this is not a modified Kaprekar number. N equals 9, n squared is 81, 1 plus 8 equals 9, the original n. R may have leading zeros. Right, the right hand part, okay. Interesting. Here's an explanation from Wikipedia about the original number. Spot the difference. in mathematics, a natural number in a given number base is a p Kaprekar number if the representation of its square in that base can be split into two parts, where the second part has p digits that add up to the original number. Oh, interesting. So p either from the left or the right side. This, in this instance, they want d, which is p's. I guess d digits is when you square it, right? Interesting. So here we're going to use the number of digits of the number. Oh, that's why it says modified. Yeah, it is special, isn't it? That's a little bit different from this property is now dependent on the number itself. Like p would be related to be like sort of log p, log of x, sort of something like that. If p is sort of log of x, add up to the original number. The numbers are named after Dr. Kaprekar. That's kind of cool. It's kind of neat. Definition properties. Natural number is if it is a fixed point to which occurs. Excuse me. Excuse me. That n be a natural number, we define the Kaprekar function for base and power be the following: alpha plus beta, where beta equals n squared mod b raised to the 1 p, and alpha equals n squared minus beta over b raised to the p. A natural number n is a b Kaprekar number if it's a fixed point for f of pb, which occurs if f of pbn equals n. 0 and 1 are trivial numbers. All b and p, all other Kaprekar numbers are non-trivial Kaprekar numbers. Example base 10, 45 is a 2 Kaprekar number. Oh, and you can change the base as well. That's kind of neat. That's kind of neat. So 45 squared is what? Oh, I see. You take a certain number of digits. This is what the modular function takes the number of digits away, I guess. Something like that. I don't know. It's a little confusing. I think I have to like sit down and really process this. But alpha, beta. Confusing? I think so. I think the alpha just shifts to the right. It's effectively like a right shift, whereas the beta. Okay, yeah, that makes sense. Oh, no, I understand now. Yeah. Okay. Right. So this is sort of like the right shift, the division, the modulo is when you take the modulo, it's like a left shift sort of, and then the other operation is like a right shift of what's left when if you take the modulo. That's very interesting. It's just sort of a more formalized way of performing that, what we described, where you take a certain number of characters on the right side and split that from the characters on the left side, and then take the integers, the results, and add those together if that's equal to the original number. And you're going to take of the square, you're going to take those values. Now what is interesting though is this modulo of beta b raised to the p. Oh yeah, that's why it's squared, because p is 2 in this instance. But in our case, what it's going to be is not b raised to the p, but b raised to the I guess the number of digits of our original value. We'll call it n. So it's going to be log of n. I think it's, how does it work? It's like the roof of log n. So if you have, no, floor of log n. So if you have 9 log base 10, floor plus 1, I think is what it's supposed to be. Yes, the floor plus 1. So a 9 would give you 1 digit, right? Floor of base 10, 9. Log base 10 of 9, the floor of that 0 plus 1 is 1 digit. If you have 10, it's 2 digits. The floor is 1 plus 1 gives you 2. Yes, that seems to make sense. So this P in our instance is just going to be, so we can actually perform these operations exactly, which is kind of cheating now a little bit. It's not how I would have done it had I thought about this previously, but we just use the same formulation here, and use, instead of P, we just let P be the floor of the logarithm of n plus 1, quantity plus 1, and then yeah, and then we just perform this operation, just perform this check, find alpha, find beta, given n, which is actually going to be n, right? This perform these operations given p with respect to n, and then check if this matches the original number, if this equals n. What is fixed point though? Oh, fixed point means that, oh, I see, that's cool. So fixed point means that, I think, means that f of x equals x. I think that's probably what that means. Yeah. More likely than not, that's what that means. Let me just check something quickly while we're... It's mapped to itself by the function. So that means that f of c is equal to f of c. Important terminating condition when consideration when recursively computing f. A set of fixed points is sometimes called a fixed set. So basically anything on the y equals x line for a given y. So continuing on here. Fixed point iteration. Anyway, so there's a Kaprekar, named after Kaprekar. 1905. He was 81 when he died. Indian school teacher. Recreational mathematics. Neat. Neat. The wonderful Demlo numbers. Ah, these are the squares of the rep units. This, I've seen Demlo numbers come up quite a few times in the some of the problems I've looked at over the years. I've seen it. Interesting. The fact that these are the squares of the rep units has led some authors to call Demlo numbers the infinite sequence of these. Although one can check these are not Demlo numbers for b equals 10, 19, 28. Interesting. How do you define a Demlo number though? It doesn't really work. Yeah, I was gonna say it doesn't really work anymore. It's only the first few or the. There's only a few of these are not all of them are actually. Not all of the squares of rep units have this property. It's pretty close, but it's not all of them. Only the first 9 numbers. Those are the wonderful demo numbers. Probably because you can consider them with just single digits. It's pretty cool, pretty neat. All right. Anyway, Kaprekar number, neat. So what's the question? Given 2 positive integers p and q, where p is lower than q, so in mathematics, Kaprekar number. Okay. Given 2 positive integers p and q, where p is lower than q. Write a program to print the modified Kaprekar numbers in the range. Interesting. Function description complete. Kaprekar numbers function. So this is considered easy. Yeah, I think so. It's between 0 and 100,000. Okay. Fair enough. So simple check is, we can use a let here and just define a couple things. So we've got alpha, beta, and we've got digits, and we want an internal function here as well. So here we'll use an internal function. We'll call it fn of Kaprekar is Kaprekar, right? Or we'll call it log Kaprekar rather than p Kaprekar. We could use p Kaprekar actually. I like p Kaprekar. That's better. It's a little more general. And this function is going to take some x and some p, and you're going to get. You're going to start with. Oh, yeah. We can do it this way. You know what we'll do? Oh no, never mind. Okay, hold on. Okay. Still figuring this one out here. So have a let, and we'll do most of the calculation for this guy in here. Sure. So we said take x, square it, right? And then we can use the square here. And then we take b raised to the p, or the basis p, which is just 10 raised to the p. So we'll use this notation for the moment. And we want, oh yeah, in our case, this is also going to be 10 raised to the p. Yeah. Is it squared? What's p? What's p in this case? Well, p, we can figure out p later. Right, well, we're gonna use log, floor of log p plus 1. So you've got this square, and what do we want to do here? So let's do exponentiation in Clojure, like Like I know how we do this in Python, but how do I do this in Clojure? And then we also want logarithm in Clojure. Logarithm. So there's math log, and there's also logarithm. Functional. Library. Clojure contrib.math. I think there's a math library for. Can I do math exp? Does that do the trick? It's probably 10 raised to the p. So we're just gonna say pow. And then modulo. So log is math log. Clojure mod. Num divide. Modulus. Mod num div. So there's alpha, which is going to be the square mod this power, and then we're going to have beta, which is going to be equal to the difference between square and alpha, and I think it's, or is it the other way around? Oh, excuse me, it's beta comes first, and then alpha is, so there's beta, and then there's alpha, which is n squared minus beta divided by the power, divided by this b raised to the p. Yeah, just pow, right? That gives you beta alpha. And then what you're going to want to do is just check if beta plus alpha equals alpha plus beta equals the original number, which is x. That's it. It's P Kaprekar. And then what we want to do is say, given, we want to say P Kaprekar of, we don't really need to, you do increment of math floor, which then becomes int of, so you take math log base 10 of, I don't know how the log goes. Shouldn't there be? Said no. Come on, Meng. Java lang math is what we need. Oh, that makes sense. Oh, I see. Okay. So this uses the Java library for logarithms. Understood. Understood. So we want to use log 10, huh? Gotcha. And what they're saying is of the sum of the argument and 1. Interesting. But they don't give us a different, you gotta use the change of base. Alright, that's fine. So that's what we're looking at here. These are Java functions that we're using. That's why. Understood. Understood. P. Oh, no. Oh. Excuse me. Now we have another function, which is log Kaprekar. We'll call it of x. And this is special because we are going to return this guy. So we use pKaprekar and we say take the logarithm of x, increment it, take the floor of it, increment it, make an integer out of it, and you're going to use that as input for p, and what you're going to use for x is just x, and then you're going to perform the normal p of Kaprekar to get us log Kaprekar. And then what you want to do is it says print, right? Print the modified. Isn't there a spot that's got to be printed to? Interesting. Sample output. Can we do, well, we can do a filter, right? Filter on log Kaprekar of the range from P to Q and see what we get here. See how we do. Wrong answer. Nice. That's a nice error message. Look at that. Holy smokes. Let didn't conform, huh? That's not true. That's not true. These are named anonymous functions. Confusing as that may be. Where is... Didn't conform to spec. Alright, where? Where is that not the truth? Let's find out. Which part of this has got issues? What if we just comment everything out, right? Or no, well, yeah. Comment out the whole thing. Come back and just see what this does. Could do nothing, right? Okay. So yeah. This is obviously part of the problem. And what if we just make this empty? is just totally empty. Okay, no problem. What if we include this line and just, well, yeah, and this line and this line, but this is going to be empty as well. So we call this function, but it doesn't do anything. Let's see what happens. Nowhere. Let did not conform to spec. Okay, that's some good information here. There's a function, there's a let, this gets called. Alright. This is wrong. Somehow this is wrong. And the reason is that apparently I cannot just simply name. Maybe I have to, must name it this way. I thought I could do this. I thought I could do this. Apparently we don't conform to spec if we don't do it this way. Well, that's kind of annoying. I rather like actually naming my anonymous functions, but okay, whatever you say. Whatever you say. I think this was the issue then. Alright. Wrong answer. Nice. No matching method. Legal argument exception. Excuse me. What? What do you mean there's no matching? What? What are you trying to say here? What kind of nonsense are you trying to pull? What kind of shenanigans trying to say to me, trying to do to me? What? What in tarnation? What in tarnation? Oh. Okay, that makes sense. Wait, really? No. Come on, man. Come on, man. It's gonna be one for exponentiation. Exponentiation. E raised this power. Oh, I see. That's why. Interesting. That's not what we want, huh? Pow. That's what we want. Pow, pow, pow. Try again. We go again. This should really be an integer, I think. Integer, integer, integer. This also yields an integer. We could explicitly mention that it's an integer, but we know it'll be an integer. The reason is because we're using modular arithmetic in a special way that guarantees that it'll always be an integer. So, okay, well, interesting enough, I guess. That's it. 1954. Yeah. Okay. Cool. Okay. Okay. What we can do is have a join of these things. Clojure dot string / join print and see how that goes. We can also add something here. I feel like this is taking me a while. Was it 7:30? When did I start? I don't know, but maybe not that much time. Let's do space. Okay. Okay. Let's see. How does this go? Oh, wrong answers. Oh, destroyed. Destroyed. Why though? Kidding? This is a joke? My joke to you? I think I know what the problem is. That may have had something to do with it. What's this test case? 400, 700. Are you kidding me? Oh, come on, man. This is ridiculous. Interesting. Very interesting. Indubitably. A little logic in here. I gotta sneeze. Excuse me. Excuse me. Wrong answer. Nice. Finland, of course. Of course. Bottom, 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 bum, bum. Bottom, 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 bum, bum, bum. Bottom, 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 bum, bum, bum. Bottom, 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 bum, bum, bum. Hallelujah. Oh, you gotta be kidding me. Really? What is this? Come on. This is ridiculous, man. Hallelujah. 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 Wait, what? Oh, we don't include the... come on, man. Hallelujah. times the charm. That's depressing. Got him. Okay. All right. Fair enough. So that's one. We want to do another 7 more of these. Hallelujah. Could do more easies. I guess that's okay. Let's actually end the stream there. That way these VODs are somewhat split up. Okay, that's not too bad. That's not too shabby. It's kind of idiomatic, I guess, or imperative, that whole thing. But I guess what you would do is you would take the pieces that were sort of split amongst multiple let commands, and you would then recombine those pieces, I suppose, into different symbols. Recombine those into, I don't actually know how you do this. Thinking of like, if you're referencing a result of a computation multiple times, that's kind of what I'm thinking of. How you would do that otherwise. I don't know. Is this still functional if I do it this way? I'm not really sure. I don't know the way that I did it, where it's like line by line, one by one, piece by piece. Curious. But yeah, so let's go ahead and let's end the stream here for this one and say thank you for watching. And that was One More Down.